We've seen that the way in which popularity is distributed can be approximated by a power law. The fraction of items of popularity k falls off roughly like k 1 over k to some power, like roughly 1 over k squared for web pages. And we see similar effects for book sales, movie box office grosses, citations to scientific papers, calls to phone numbers. All of these have some built-in natural notion of popularity, how much attention a thing gets. And they all sort of fall off like 1 over k to some power. So if this phenomenon is this ubiquitous, there ought to be some conceptually clean, fundamentally simple explanation for why it's there. And what we want to argue now is that the idea that people imitate each other's behavior can in fact give us a very simple model that produces power laws. So that's what we're going to do. We're going to study a simple sort of imitation model for popularity and show how power laws come about, or at least argue that power laws are going to come about. And the underlying point here is that imitation sets up a kind of rich get richer dynamic, right? So if a bunch of people are making decisions, they're deciding what book to buy or what web page to link to, and now I'm going to come along and I'm going to make my decision by copying what earlier people have done, then books that are already popular, well, I'm more likely to find out about them. I'm more likely to copy someone who's bought a popular book, and so it'll get even more popular, right? The rich will get richer. Whereas a rare or obscure book, if I'm going to copy someone who did that, I have to find one of the people who actually bought that obscure book. It's hard to find them, harder to copy them, and so things that are less rich stay poor. That's the idea of a rich get richer dynamic, right? And that copying naturally sets up rich get richer dynamics. Okay, let's talk about how this model would work in a very, very simple stylized model for the growth of the web. Okay, this is not designed to actually capture the real way in which the web grows. It's designed to simply be sort of a metaphor for how this rich get richer process works and how copying produces it. Okay, so in our stylized story, we imagine an artificial web in which web pages are created in order. We'll number them 1, 2, 3, 4, and so forth, right? Pages arrive one at a time. And when each new page arrives, it creates one link, and it links to some earlier page. Now the whole question is going to be, how does it link to an earlier page? Right? And we'd like to argue that copying and imitation in this linking process is going to produce some pages that get very, very large in degree, very large number of incoming edges. Okay, so here's how the process of linking is going to work. So a new page has arrived. So say page J shows up. In this case, J equals 5 in my picture. And it's going to choose where it's going to link. It's going to choose to link to one of pages 1, 2, 3, or up to J minus 1, one of them. It's going to link randomly, but not completely uniformly at random. Rather, it's going to be controlled by this probability P that we're going to set in advance. And it's going to do one of two things. So with probability P, page J is going to do something very, very simple. It's just going to link to one of the earlier pages chosen uniformly at random. Okay, so there's no copying, no rich get richer. It just reaches out into the world and samples something completely uniformly at random. So here, for example, page 5 linked to page 2, and that was actually the first incoming link page 2 ever received. Right? So page 2 was not rich in popularity in any sense, but it got this link just because page 5 found it by accident. Okay, that's with probability P. With probability 1 minus P, a new page is going to do something more complicated. And let's illustrate that with the next page to come along, page 6. With probability 1 minus P, the way this new page is going to link is by copying. So first, this new page J is going to choose an earlier page uniformly at random, some page I. Right? So maybe page 6 chooses page 3 uniformly at random. And then it's going to link to the page that I links to. It's going to copy I's decision. So when 6 copies 3's decision, it's going to link to page 1, and 1 gets yet another link. Okay? And that's the whole process. The pages come in order. Every time a page shows up, it flips a coin. And with probability P, it just makes a uniform random link. Doesn't matter what anyone else did before. And with probability 1 minus P, it picks a earlier page uniformly at random and copies their decision. Right? Copying their decision means links to where they link to. Now, notice how this really captures in really very succinct form how copying sets up the rich get richer process. Because think about even the picture we've drawn, right? Page 1 has many links coming into it. And so if a new page comes along and decides to copy someone's decision, it's more likely to copy a decision to link to page 1 than to any other page. And if you think about it, that's actually sort of in very stylized form what's happening when we create web pages, right? You're more likely to find out about popular pages. So when you create a page, when you write a blog post or something, you're more likely to link to stuff people already know about because you're copying them. Okay, so this is copying, this is the rich get richer dynamic, and it's a very, very simple model. And it's simple enough that actually one can analyze it. And we're not going to do that here, but I'll state the central fact that emerges from this, which is that if you run this process over time, then the fraction of nodes of in degree k ends up scaling like 1 over k to a fixed power, 1 over k to the c, where c is a constant that depends on p. It makes sense that it should depend on p. Because after all, p is sort of like a knob that I can turn. And if I dial p all the way to 1, then we see that everybody just spends all their time linking uniformly at random. There's no copying going on. And so in fact, as p approaches 1, the popularity distribution becomes very diffuse and it's very hard to find popular pages. Whereas when p gets very small, almost everybody is copying all the time. And so we get these wild imbalances in popularity, right? Very popular pages become very likely because there's so much copying going on. So in effect, the amount of copying is controlling the exponent on the power law distribution. And that exponent is in turn telling us how spread out the popularity is, or how much it's concentrated in only a few nodes. So that's the basic model. That model is sometimes called preferential attachment because people attach preferentially to the more popular items. But I think it's easiest to think about it as just a story of imitation and the feedback effects that produced. Now, the simple model, of course, is much too stylized to capture everything that's really happening in the creation of web pages. And there have been a lot of work extending models of this flavor, right? Taking into account the fact that pages are created simultaneously. Pages can disappear as well as appear. Some pages are simply just better than others and they attract links more readily. Right? All of these are things you could put into the model to try to make it more realistic, more resemble what's happening in the creation of web pages. But I sort of like keeping it simple for this description now because in its extreme simplicity, this model captures an essential fact. Right? And that essential fact is that anytime there's imitation, that sets up a rich get richer dynamic. And once you have a rich get richer dynamic, that's very naturally leading to these non-dependent choices, right? These feedback effects that produce power laws.